us. She is currently a postdoc here at Caltech in the Astronomy department. She hails originally from Chile, where she did her undergraduate and master's studies at the, I'm gonna mess up the university. Pontificia.
Universidad Católica de Chile.
She did her PhD at ETH Zurich, the same institution where, wasn't ETH where Einstein was? Einstein was, he was faculty there? Yeah, and student there. And she's been a postdoc at Caltech for the last 2 years, and is shortly leaving us to become to become a postdoc at University of Paris. So this is like her last hurrah here. Bonjour, indeed. And she's a world expert in the cosmic web and cosmological observations of various different structures throughout the cosmic web. So please welcome Sofia Gallego.
Thank you very much, Cameron. Thank you very much for everybody coming here. So many people. I'm so excited. I hope by the end of this talk you guys understand why we astronomers are so excited about the universe at a large scale. What does it mean that the universe is so big, so large? What implications have in the formation of the universe, of the formation of us, and what is our place in the universe? So this that you see in the background is a video of a simulation of the universe. You know? So we have galaxies, we have stars, we have gas collapsing and forming this very structured matter. But how do we came to realize that is a universe, how the universe looks like? Actually, the story began very, very close to us, actually. About a 46-minute drive from here, literally, because I Google mapped this. So there is this very little mountain very close to us called Mount Wilson. And about 100 years ago, yeah, in that observatory mounted in that mountain, this was the biggest telescope of that time. And there was this guy called Edwin Hubble that was casually working at that observatory. And he realized, actually, that many of these fuzzy things that were in the sky were actually galaxies, things that were very, very far away. For example, Andromeda was a full galaxy, and there were many, many others. So he got very interested in these things, and he wanted to study it, like we astronomers do, and understanding them in a statistical way, so measure the properties of many, many of them. So once he did this, he got very curious about two properties of these galaxies. First of all, how far away the galaxies were from us, and second of all, how fast they were moving with respect to us. And then he came out with a very blowing mind realization. It's really, really blowing mind. You see, there's a very, very tight correlation. You know, the farther away those fuzzy things are from us, the faster they are moving. And I guess you actually know the answer of this, right? What is the implication of this? The universe is expanding. It's literally blowing mind. It's fantastic. For me, it's one of the most spectacular realizations of the whole modern astronomy, maybe in science. So how do we, actually, the expansion of the universe has very, very interesting implications for us astronomers and also for you. So I will try to explain something. And for this, I will need somebody to hold my microphone. Yes. So I created the universe expansion measurement device. So what you see here are actual Caltech brains, but they are supposed to be galaxies. Okay, so bear this with me. I require a lot of imagination from your part. Okay, so this is a galaxy, this is a galaxy, this is a galaxy. And imagine that we are here on Earth and we're trying to measure a galaxy, okay? So the same galaxy, if it's double the distance to us or triple the distance to us, and the universe is expanding, the faster it will move with respect to us. And because of that, and because the light takes trouble to come to us, as you can see in that image, the light that is coming to us will get expanded, stretched out, and it will look redder and redder and redder and redder. I did this today. So, thank you very much. If we're observing, again, I will do the same explanation here. So we have a galaxy, the same galaxy, the same galaxy, the same galaxy. The farther away it is, the redder and the redder it looks. And we can measure that. It's a very easy quantity to measure. We call this cosmological redshift. And why that? Because it's redshifted. There's a shift of the light to the red color. And it's also an equivalent of distance, because the farther away the galaxy is, the redder it will look, and it means that it's farther away from us. But it also measures epoch, because light takes time to come to us. So the farther away the thing is, the farther away in time it is, because we are looking at the galaxies when they were very, very young. So actually, having this and understanding the expansion of the universe, I will show you an equation, guys. I'm so sorry. I will apologize in advance. But it's a very cool equation. Do you guys understand what redshift is, right? Yes. Universe is expanding, things are moving to the red. Yes. So this is the equation of the universe, guys. Yeah? Oh. When you're having parties with your peers, you have to ask, guys, you know, I just saw the equation of the universe. I'm so cool right now. Yeah. This is really cool, because this equation of the universe tells us that depending on the relative proportions of the components of the universe, we know how the universe evolves. That's so cool. That's so freaking ridiculously cool, right? So, yes, equation of the universe. So now, we are going to cook a universe, okay? So this is a recipe for any universe, you know? So if we know the relative components of everything, like when you're baking a cake, if you put too much of something or too little of another, the cake will end up in a very different thing, right? So, the first part of these equations, omega R, that's kind of the radiation, the light. You know, it's like the energy you give into create this cake. You also have omega matter, and that's the dark matter that we hear in the previous talk, but also the baryonic matter, that one we are made of, the galaxies are made of. So that's like the flour of the cake, you know, like the substance of the cake. We have something else that's the curvature of the universe, and it's a super weird thing, and bear with me, this is not the perfect analogy, but it's like, maybe you can have a flat cake, or you have a curved cake, and depending if the cake is flat or curved, the cake will be cooked in a different way, okay? And there's also the dark energy, or some people call it the cosmological constants. We have no idea actually what it is. But the analogy here is like, it's the yeast, you know? It's what you put there to make it expand. So the more yeast there is, the larger and larger the cake will become. So, okay, that can make any universe. Actually, also has great implications. Like, can you help me again? Okay, thank you, Susan. So, if there is a lot of matter, okay. If there is a lot of matter, maybe the universe will expand at the beginning, but then it will collapse, and become one thing again. If there is a relative nice proportion between matter and the dark energy, it will actually do this. But if there is a lot of yeast, everything will move away from us, everybody will hate us, and they will do this forever and ever. Do you know what the answer is of this? Oh, there's another thing I totally forgot, and it's very important. Pay attention. This is like the measure of this equation today. So these measure how fast away are proportionally things moving from us. For example, if an object is around 1 megaparsec away from us, if we move away from us at 70 kilometers per second. And because, guys, we're in America, so I did the effort and transformed this in miles per second per light year, per mega light year. Okay? So actually, if a galaxy is about like 5,000 megaparsec from us, it will move faster than the speed of light to us, and we will not see it anymore. And that's why there's a limit of what we can observe in the universe, okay? Bear with me. So the answer of what is our universe cake made of, we have a lot of dark energy, we have a lot of G's. So the universe really, really hates us because everything is moving away from us, not only moving away, but also moving accelerated. There will be a moment in time in which we will not be able to see almost anything except Andromeda, who will collapse with us, and we will become one. But that's another story. We also have a very, very large amount of dark matter, and we hear a lot about that in the previous talk. And we have very little, regular matter like we are, And even from that, very little of that is stars, is galaxies, is dust and gas, the things we can actually see and measure as astronomers, mostly. And, well, the other parts of the equation, apparently the universe is flat, not the Earth, the universe. And the amount of radiation compared to the other components is almost zero, so we don't use it in technical and linear equations. So now there's more equations, guys, I'm so sorry. So now, we have the same equation that tells how the universe evolves, the scale of the universe evolves. But we also, we go to a computer, we input all of these equations that tell us how the gravity interacts with things, that glue things together. The gas, like the gas interacts with dark matter, but also interacts with light, because it's visible to light. And we have radiation, and this is very complicated. We put all of these things together, and we make it evolve in time. So this is from the beginning of the universe, initial condition, like far away there, it's the end, like today. And we see an evolution, there was nothing, and their structures start to form. They look like filaments, and there are filaments in 3 dimensions. So the realization is that matter is predicted to resist in a large filamentary structure that we call the cosmic web. And that's, the intersection of those filaments of the large-scale structure are the densest parts of the universe, and are dense enough to form stars and to form us. But even with the latest images we have ever gotten, like deepest image of the universe that we have today, the James Webb Space Telescope. Look at this image. It's full of galaxies, stars, and other stuff. Where are the filaments? Why they're not there? Well, the answer, it's because they are not dense enough to form stars. So they are invisible to us, and they're mostly made of dark matter. So the only way, the only way we're trying to figure out this, or the first evidence we have of these filaments beyond the galaxies, was because of a forest, okay? Whoa, sorry, forget about this. So imagine you have a very, very distant object that is so bright that the light arrives to us. But we are looking at it through a forest, because there are things in front of that light that is covering, so we cannot see the full light. So that is what's happening with the things called quasars. Okay, they are super bright objects, very distant, very far away, very high redshift. Remember, redshift, distant, time with respect to us. And because we're a forest, and the forests are hydrogen clouds that are part of those filaments in between the quasar and us, they are blocking the light a little bit in different wavelengths and different colors of the light of the quasar. And that's how it looks like in real life. So that's a spectra. So that's the intensity of the light that we measure at different colors of a quasar. That's the Lyman alpha light, which is the emission light of the neutral hydrogen. It's a transition line. It's just like light, it emits, hydrogen emits when it absorbs light or emits light. And after that, you see there are like spikes, of absorption thingies. And that's the forest. And they discovered and realized that was part of the large-scale structure of these neutral hydrogen clouds that were between the quasar and us. And we've not only discovered that, we also discovered that the forest was much more dense. The earlier in the universe, there was much more hydrogen, neutral hydrogen, the farther away in time we were looking at. So the universe is not like only made of a large-scale structure, there's an evolution of the structure. The forest is denser at the early of the universe and is more faint, closer to our epoch. So, okay, we saw this evidence of this forest, but it's only in the line of sight, it's a dot of information. What if we want to know the 2D, like the spatial information of how this matter is distributed? What we try to do is, because we knew that this matter was around galaxies, because galaxies are very dense places in the universe. So there's supposed to be a lot of gas around these galaxies, but we didn't see them individually. You see, there's a lot of very beautiful pictures of galaxies here, but if you look beyond the galaxies, nothing, you know? So what my current advisor did, he was very smart here in Caltech, he combined many of these galaxy images and put them all together. It's like, for example, when you take a large exposure picture of the sky, the more time you integrate, the more details you see. You know, but we don't have time to look at just one. It's better to look at many of them and combine them together. So that, we call it the UV, is the light of the galaxy. But if we look at Lyman alpha, again, the line of the hydrogen. Whoa. It's much larger, it's larger than the size of the galaxy. So that was the first evidence of the cosmic web in 2 dimensions around the galaxies. We call this the circumgalactic medium, because it's around galaxies. And then, okay, guys, I lied to you. I really lied to you. I mean, it's astronomy talk, right? You want to see the pretty pictures, I showed you the galaxies, but this is how galaxies actually look like. Because they're so far away, we don't see many details. So I had to, most of my time, actually play with very boring pictures. Yeah, I'm sorry. But by the time I started my PhD at ETH Zurich, there was a new window to the universe. And we call these integral field spectrographs. And we call that because they allow us to see the universe in 3 dimensions. And why is that? Because these detectors not only see a 2D image of the sky, they see for each pixel, like the ones in our cameras, for each pixel of that CCD, we have the information of the color. So we have a cube, a data cube of information. Can you hear me? There's a lot of background noise. Special effects. Okay, so with these, we can see the universe in 3D because we have to have information of the color in each side. So it allows us to detect better the signal of the galaxies or the cosmic web with respect to the noise. Okay? So the idea now is that, okay, we have the light of the galaxies that are very bright. We understand galaxies very well. There's a whole field of galaxy evolution. But what we don't understand is how to connect the large-scale structure with the galaxies. So this is a picture of how we understand or believe the context around the galaxies is. We have the galaxy at the center. We need accreting material from these filaments, from this large-scale structure coming into the galaxies. And at the same time, the galaxies have a lot of energy, a lot of radiation that shoots out around, you know, and also interact with this large-scale structure. But we see that in simulations. We don't see that too much in observations. And that's what I was trying to do. So finally, okay, I will show you a little bit of my science. So this is a Hubble image of this space at a very special epoch of the universe that we call the cosmic noon, because it's about at the half of the age of the universe. So the Hubble telescope sees only dots in the sky, okay? But if you go to Lyman alpha, with one of these 3D instruments, which is KCWI, the one in the right, which Caltech is part of the development of this instrument. It's actually in Hawaii. It's very cool. I have never been there. I wish I could have gone, but I didn't. So this instrument is capable of detecting extended emission, this circumgalactic medium, around these objects. And they're super cool because they're not only isolated galaxies. They live in a group of galaxies. So we can see together the galaxies and their medium. You know? So these are the 2 things together, okay? So that's, in the right side, is emission in Lyman alpha, again, the line of the hydrogen in emission. And that's the Hubble picture, okay? So we can compare these together and trying to understand much better this interaction between the large scale structure and the galaxies. And the cool thing about this, because I've told you, it's an instrument in 3D. So imagine that each of these pixels, we have the line shape of Lyman alpha, okay? The line at different colors looks like this, like a Gaussian. It's like a little curve. We can also have the information. This is information of the integrated emission. So like the collection of all the light. So it's the area under the curve. We can also, well, because that's the total emission, right? We can also have an offset. right? With respect to a middle point that you define, the line could be moved, and we can measure the offset of the peak of the line. And also, we can have a line that is narrower than the median or wider. So we can measure the width. That we cannot do it with normal telescopes, only with these kind of instruments, 3D objects. So now we have 3 different pictures of the same object. And here on the right side, you have the Hubble image. So you see the galaxies, and you see a very bright, dense galaxy in the middle, a lot of tiny things which appear to be satellites of this galaxy. And then you see, this is a very rich information. It doesn't tell you about this, not only tells you about the structure and intensity of the light, but also how displaced the line is and how wide or narrow the line is. And that has a lot of information about. I have no idea what it means yet, actually. But it tells you something very interesting. Actually, if you kind of overplot the previous image, it appears to be that something very active is happening there. You have this galaxy that is accreting maybe gas from the satellite galaxies, and it's absorbing that material. Maybe there's, like I mentioned before, this quasar, these very bright things in the universe, shooting out light and interacting with the hydrogen that is here and heating it up. And we don't know. That's the worst part of all, because this line, if I want to go to the details of the theory, it's extremely complicated to model. So even current, very sophisticated simulations that actually Cameron works a little bit on that, they cannot reproduce this. So this is an incomplete picture yet. There's a lot of things to understand. So my mission, like now and in the future, is to try to understand not only the large-scale structure, but to connect the big picture, these big filaments of the cosmic web, with how we evolve, or how galaxies evolve. So I hope, now is the end of my presentation, that you understand what is the cosmic wave, why do we care, what are galaxies. Thank you very much. Oh, yes, sorry, sir, yes?
Are you taking questions?
Yes.
So, there's the acceleration due to gravity that's keeping things at a certain scale clumped together because they're pulling the pieces together because of gravity, balanced at a certain point between the acceleration due to the expansion of the galaxy. And so there's got to be kind of a middle point.
Okay.
And can you see that in the filament structures between the large-scale objects?
It's a very good question. I will say it for the rest of the people here. So what he says is like, okay, you have the expansion of the universe, but you also have things that maybe are close together that interact in a different way. And if there's a tipping point besides expansion, because I told you guys that Andromeda is collapsing with us and becoming one big galaxy. First of all, what accelerates things outwards, it's the dark energy. Gravity actually is attractive. The only thing that compensates gravity besides dark energy is the pressure from the photons. The photons produce energy and pull things together. It's a fight between pressure and gravity. And actually stars are formed because the gravity is so much that they fuse things together. Or black holes are produced because the pressure, from the things that are tied together doesn't compensate the gravity and they collapse, right? And interestingly, yes, there is a point in which if the gravity internal, is bigger than the pressure of the universe expanding, they form a group tied by gravity. And for example, what I was showing you here, this group of galaxies are protoclusters, which are the beginning of the most massive structure of the universe, which are called galaxy clusters. And these groups are tied by gravity. So they are decoupled from the expansion of the universe, and they interact together. So Andromeda is coupled with us. So gravity wins against the push of dark energy. So that's why we can collapse. Yeah. But very good question, yeah.
So at the tipping point, do you see structures, those filaments between these large scales that you can see might have been caused because it's at a tipping point?
I don't know exact answer. I think the answer is no, but maybe. If there is something, it will be something that we cannot detect, yeah. But I think I have seen some simulations in which they show some kind of rings that may be related to the because okay, when things are tight, after time they become spherical objects. And kind of the border of those objects may be a transition point in which you can see something, but the answer is I don't know. I mean, it's like if there is something, it's very hard to detect. Yeah. Okay. First, the person in the very back. Can you please shout your question? Or come? Do you want to come? I can come to you. Can I? Sorry. Sorry? Okay, dark energy and dark matter. So we call them like that because we are very ignorant. We have no idea what they are, basically. So we call it dark just because we don't know. But they are probably very, very different things. So there are many theories of what dark matter is. It can be like a particle that we don't know, that doesn't interact with light. It can also be like a modified version of gravity. So like Newton and Einstein are wrong, and there's something else that tells us how the things move and evolve. And dark energy is even more mysterious because it's all around us. We don't know if it's like also some kind of property of the universe, or it's like a particle or something, or just a constant of the universe. We have zero idea. Yeah. Yes?
You share with us a recipe for a universe, but I thought there was only one universe, but it seems that there is more than one universe.
Oh, that's a very good question. The answer is we don't know. I'm sorry. Yeah, I mean, technically there could be many other universes. We don't know because what we don't see, we cannot prove. I mean, we scientists can only say things about what we can measure. There are some attempts, some crazy theories around that maybe a previous universe before us leave an imprint in the cosmic microwave background radiation, but it has not been proven yet. It can be, but we don't know. Maybe the multiverse exists. Yes?
Okay, on that question, on the cosmic microwave background radiation, the blue spot, is that the sign of another universe interacting with ours? I read another.
So I think he's asking if there's an imprint on the cosmic microwave radiation of another universe. We don't know. That's a short answer. We have no idea. I mean, some of the imprints, that's something I took out from the presentation because it will become too long. But we can measure the relative constituents of the universe thanks to this microwave background radiation. So it's a very smooth radiation, but there are some kind of fluctuations on this energy of this background. Depending on how sharp, how intense, or how less intense they are relative to a certain scale, they will tell us how much gravity how much matter there is, how much light there is, and many other things. Yeah. But until now, we have no know yet if there is evidence of other universe in that imprint of the universe. Okay. Thank you, guys.
Thank you, Dr. Sofia Gallego. All right, we're going to have